inform electrical utilities. So before getting started, I want to give a brief introduction about Dr. Stephen Quiring. Dr. Stephen Quiring is a professor in the Atmospheric Science Program, Department of Geography at the Ohio State University. He's also a fellow at the Risk Institute at the Ohio State University Fisher College of Business, and a member of the Translational Data Analytics Institute and the Sustainability Institute at the Ohio State University. Dr. Quiring is the president and co-founder of Storm Impact at the Ohio State University technology startup that provides data-driven machine learning models to electrical utilities to support their pre-storm preparation and long-term hardening activities. His research focuses on hydroclimatology, weather data analytics, and modeling the impact of storms on electrical infrastructure. Specifically, he's interested in examining land-atmosphere interactions, drought monitoring, seasonal climate forecasting, and soil moisture. He's also interested in examining the impacts of climate change on businesses and organizations. His research uses in situ observations, remote sensing, and models. He also leverages AI and machine learning models to model the climate process and impacts. Dr. Quiring has a very long list of achievements, so I'm going to name a few in here. For example, he has published more than 110 journal articles and received over $15 million in funding from the federal and state agencies, including an NSF Career Award in 2010. Dr. Quiring is currently an editor in the Journal of Applied Meteorology and Climatology and an associate editor of Physical Geographer. So without no further introduction, because Dr. Quiring do have a long list of achievements, and I believe everybody is as excited as I am right now to hear more about his research. So let's welcome Dr. Quiring, and now the floor is yours.
Thank you so much for that kind and generous introduction and for the invitation to present today at this UCGIS seminar. I'm looking forward to telling you a little bit more about some of the work that I've been doing, and especially welcoming your questions and discussion and feedback at the end of the talk. So to start, to provide some background on the topic today, this is a figure that is fairly familiar to many of you from the National Oceanic and Atmospheric Administration. And this is a very nice summary of the impacts of weather in the United States between 1980 and through the end of last year. And this particularly focuses on those major weather events that caused more than $1 billion in losses to the US. And there's multiple pieces of information that are incorporated within this, but just to orient you, on the left-hand side is the number of events. And so classified based on the type of weather conditions that caused those losses, you can see that in 1980, there were 3 events, and those were comprised of a tropical cyclone or hurricane, a flood, and a drought, and that there's a very clear pattern over time. And these have already been adjusted for cost of living. And so the secular trends that are shown here are not a function only of the increasing cost, but actual real increases in the frequency and severity and impact of weather events. And so if we look at the latter part of the record here, since about 2010, you can see that there's a very clear pattern of increasing numbers of extreme events, and especially those in this green category. So that's the severe storms, and the yellow category, the tropical cyclones or hurricanes, and that floods and droughts consistently are also present throughout the entire time series and in recent years and decades. And so this kind of provides the background or context for what I'm going to talk about today. And as a climatologist, there's lots of things, there's lots of research that could be done related to this. And my interests touch on a variety of different aspects of that. So we could look at the physical climate system and try and understand how and why the frequency and severity of these events are increasing. Or we can focus on how to leverage information about these weather and climate events that would help organizations, communities, and companies prepare for, respond to, and hopefully mitigate some of the impacts of these weather disasters. And that's really the work that I have focused on over the last number of years, both at Ohio State and then, as Leigh mentioned, with the technology startup Storm Impact. So today my focus is on impacts of weather and climate on the power system. And so we can go from all billion-dollar weather disasters now to focusing on those events that are specific to the electrical power system in the United States. And the Department of Energy collects information. In fact, there's a federal reporting requirement that requires electrical utilities to report anytime there are disruptions. And some of those disruptions are non-weather related. So things like acts of vandalism or equipment failure or automobile accidents that take out electrical infrastructure. But when we look here at the top graph and say, what fraction of the total number of customers interrupted in a given year can be associated with weather events, we can see that weather events are, by and large, the largest driver of power outages in the United States. And that's been pretty consistent over the last couple of decades. And if we average this overall, about 83% of the customer interruptions are as a result of weather conditions. There are also lots of other events that could be of interest related to cybersecurity and vandalism and automobile accidents and other things. But today I'm going to focus on the weather-related impacts. We can also use those same reports from the Department of Energy to look at what the causes of those major power outage events are. So here, a major power outage event is more than 50,000 customers interrupted. And I use the term customer because a customer is a meter. So if you live in a house that has its own electrical meter and you pay the bill every month, there might be multiple people within that house, but to the utility, it's a single customer or a single meter. And so here, when we think about and report the number of customers interrupted, if you want to convert that into a population, so looking back at this last graph, and if we say, oh, there are 20 million customers affected in 2004 by major power outages, you need to multiply by about 3 or 4 to turn that into a population. So this would be 60 to 80 million people that were actually affected. And so on this slide, we're looking at the causes. So which events occur most frequently? And now if we just focus on the inner circle here on the left-hand side of this plot, this is the number of events. And we can see that tropical activity, tropical storms and hurricanes account for about 20% of the major power outage events. Severe storms, thunderstorms, account for about 47%, and winter storms account for the remainder. But if we're looking at which events are most impactful, so not just the frequency, but the impact or severity, how many people lose power, we can see that this shifts so that even though hurricanes and tropical storms occur relatively less frequently than thunderstorms and winter storms, they are the largest driver of customers interrupted. That's because while there are relatively few that occur every year in the US, when they occur, they can cause significant impacts. And so in fact, when we got into this field and started developing models for this, our models were focused only on hurricanes because they are such a major disruptor to the power system and cause a great deal of damage and also take a long time to restore the power. As geographers, we might also be interested in looking at the spatial patterns around this. So we can look at the spatial patterns as it relates to the number of events, or the spatial patterns that relate to the number of customers, the number of meters that are affected. And when looking at those spatial patterns, there's obviously multiple things going on. One is the risk from weather itself. and the other is the exposure, so how many people live in those areas. So in general, these patterns are determined by the more populous states obviously tend to have more customers interrupted per storm, and areas of the country like the Gulf Coast and the Midwest that see more frequent thunderstorms and winter storms, and along the Gulf Coast and East Coast where hurricanes play a role, those are the places that show up in terms of the spatial patterns. And I should mention today, when I'm showing the results from our models, they're typically focused on particular utilities, so electrical utilities that have shared data with us, but the methods that we've used could be developed and applied to anywhere in the United States or in the world. And I have a couple of examples of the global work that we've done. So why might electrical utilities want to invest in data-driven machine learning models to help them make better decisions? And this really comes down to costs. And so they are primarily investor-owned. And so that means that in a given year, they want to see that the revenue they receive exceeds the costs of running their operation, and storms are a major cost. And so in the bottom left-hand corner, you can see that based on a survey, a benchmark survey done by First Quartile of 35 utilities in the United States, the average tropical storm for the average utility will cost them something around $40 million to restore from that event. And this accounts for all of the extra people they need to bring in, all of the additional overtime they need to pay, and the equipment, the replacing the broken poles and transformers that are affected by those storms. You can see, however, that there's a great deal of variation. And so there's a very long tail on this, and the upper limit could be hundreds of millions of dollars for very large hurricanes affecting a large utility. And the other thing that's of interest for motivating utilities to purchase models that can provide them with advance warning about what's going to happen is they need to make decisions related to staffing levels. And so how many crews will they need for restoration? And they need to make those decisions ideally prior to when the storm occurs, because if they're bringing in contract crews, and most utilities don't have enough personnel in-house to restore and respond to storms just with the people that work for that company, they bring in contractors from that go to many different utilities, or through mutual aid, they borrow crews from neighboring utilities or states that are further away. So for example, if a hurricane affects Florida, the Florida utilities may ask for crews from Pennsylvania or New York that are not going to be affected by that storm to travel down, bring their trucks, bring their equipment, and help them do restorations. And so that's what is reflected right here, where you can see that often the number of crews that are brought in externally are 1 to 2 times greater than the number of crews that are internal. And this drives costs because you're paying people double overtime and to drive down from far away, and you're putting them up in a hotel, and you're paying for all of their meals. And so a lot of the storm restoration costs are driven by this, by the people part. A additional motivation is around the regulatory scrutiny that utilities receive. And so while they are investor-owned companies, for the most part, they need to respond to state and federal regulators who oversee the operations of utilities and who need to approve things like the rates that they can charge to their customers, and also the cost recovery that they might try and recover post-storm. And so something that's become increasingly important in recent years is the timeliness of restoration. So if you lose power at your house, it's a major disruption and also potentially really costly to you personally. If you have a freezer full of, I don't know, expensive steaks, if you are planning to work from home and can no longer do that. If you are, it could also be risky if you have a medical or electricity dependent medical device, you're on oxygen, or you have other medical devices that you need that run off electricity. And so the longer the restoration period, the more unhappy customers get and the more regulatory scrutiny. And of course, longer outages also mean more lost revenue. So when your power's off, the utility is not making any money from you. You're not using any electricity, so they can't charge you for that time. And you can see that tropical storms here are the ones that typically require more than 150 hours, but sometimes as many as 350 hours. So days to weeks of restoration from some of these events. All right, so that's some background. Let's talk about the different kinds of models that could be developed, or the different kinds of decision support tools that utilities might be able to leverage to inform their decision-making process. And there's really multiple decision-making timescales. So the one that I've talked about so far is in the hours to days prior to a storm occurring. And this is what we call pre-storm preparation. So determining how many crews they need, where to place them, and what materials they might need. So how many poles are going to be blown over, how many transformers are going to fail, and to optimize that pre-storm preparation and post-storm response process. The second is on much longer timescales. So this could be seasonal to interannual to decadal. And this refers to long-term hardening and mitigation. So for example, in hurricane-prone areas, utilities may decide that it is too risky to have electrical infrastructure above ground, and it might make sense to bury power lines underground so they're less susceptible to storm-related damage. They may also want to shift from wooden poles to steel or concrete. They may also take other steps, things like distributed generation or lightning protection devices that can reduce the impacts of weather on the power system. And so the models that we develop can be used at multiple timescales, as is shown on this slide here. So on the left-hand side, we start with the long-term decision. So looking out years or decades to answer questions like, how will climate change influence the frequency and severity of weather-related hazards like hurricanes on our utility system? And therefore, should we take different strategies in terms of hardening or preparation, and that when we're reinvesting in our utility infrastructure, maybe we don't want to just replace a wooden pole that fails with another wooden pole, but we want to change how we're planning our utility infrastructure. There could also be seasonal decision making. So as we're approaching the 2023 hurricane season, well, how are things looking? What does the National Hurricane Center or Colorado State University or the other seasonal hurricane prediction groups, what are they saying about how many hurricanes might occur this year? How many might make landfall, how intense they're going to be, and can we use some of that information to inform our seasonal resource planning? Like maybe before a big hurricane season, we're going to go out and trim vegetation along utility right-of-ways to help reduce weather-related impacts. And then there's the pre-storm response timescale. And that's what I'll focus on today. But just know that these other timescales, the same types of models, can also be used and developed for seasonal or for interannual to decadal planning. So in terms of how utilities typically look at the pre-storm preparation process, often the people who are using our models are part of the emergency preparedness organization. And as part of that, they are doing things like tracking the weather, communicating information to their customers and to their staff to keep them safe, using storm models to identify what the potential impacts might be on their utility, doing things like resource planning, so pre-storm, positioning crews and assets and bringing in contractors from other companies, And so what I'm talking about today that helps support this process is the storm modeling. So rather than just relying on the expertise of the utility staff and their experience saying, oh, I was around during Hurricane Harvey and we had 500 poles that were damaged, so this storm looks similar, so we're going to estimate that we might have a similar impact. We can leverage data-driven machine learning models to actually do a better job of both predicting conditioned on the weather forecast and also characterizing the uncertainty in those events. And so when we think about the timescales that we're typically thinking about, this is often days in advance, because once we're a few hours before landfall, if we're talking about a hurricane, or a few hours before severe thunderstorm onset, that is the time to shelter in place. You do not want your staff out exposed to the weather conditions. You want to keep your people safe. And so mostly the optimal time scale is in that 72 hours to 48 hours in advance, where they really want to know what's going to happen so they can adjust their resource allocations and think about what order they're going to do restoration in and where to have their crews staged prior to the storm, and do they have enough materials to respond. So how do our models work? This is an overview of our model development process, and the screenshot at the bottom is the dashboard that our customers, in this case for the technology startup Storm Impact, this is the dashboard that they can access. And in fact, today we are going to see potentially some severe weather. And so there's lots of activity on our dashboard today and in preparation for tomorrow throughout the Midwest and the southern parts, and some of the utilities that we serve in the eastern United States are very interested in monitoring the weather conditions over the next day or so. So what we do to develop these models is to collect data from the utilities. So every utility has an outage management system that records where and when customers lose power, the duration of that outage, and then when that outage is restored. And so that gives us information on the location, the duration, the frequency of damage and customers interrupted. And here we would like to have as long a record as possible, since these are data-driven machine learning models, and we're really interested in the extremes. And so getting the highest impact events right, correct in our forecasts, so this is way off in the tails of the distribution, means that we have usually very few of those events if we have even 5 years of data. And so things like Superstorm Sandy or the 2012 derecho are super important for accurately training models and making sure that they can predict events that they haven't previously seen. And then we generate a very large feature data set that includes both meteorological observations, soil moisture information, which turns out to be really important for power outages, environmental variables, so vegetation, land cover, slope, aspect, information from the Storm Prediction Center, and then a lot of information from the electrical utilities. So most of them have a geographic information system where they track things like where every pole in their system is, and the age of the pole, when it was replaced, who replaced it, does it have any other equipment on it? So sometimes utilities share poles so that it may have some hardware from Verizon or from another utility on a pole owned by an electrical utility. And so there's a large amount of information in both raster and vector format that we ingest as features into the model. Then there's a variable importance and training exercise to determine for that utility, for different types of weather, which variables are the most important. And then we do a lot of testing of different methods, and I'll highlight some of that later in my talk. So what kinds of machine learning methods might we use? How do we do sampling or oversampling or undersampling of those to account for these rare but high impact events. And then thinking about things like what is the spatial and temporal resolution of our models so that it's optimum to meet decision makers' needs. So in this case, in this example right here, showing the first energy service territory, each of the polygons here is a district, and our predictions are for a 24-hour period from midnight to midnight. And that's what this utility found most useful in terms of the spatial resolution and the temporal resolution of the analysis. After we build, validate, and deploy these models, we then routinely monitor their performance. So in fact, we meet with all of our customers every month or every quarter and do a post-storm assessment to say, how well did the model perform on recent events? So we'll be watching really closely over the next 48 hours to say, how well are our predictions for today and tomorrow, how well do they validate versus what actually occurs? And then we retrain the models every month once we get the actual conditions from the electrical utilities. So in terms of a schematic, to kind of put everything that I described in words into a picture, this shows visually how we develop and build these models. So on the left-hand side is all of the historical information that could be at a grid cell or could be at a polygon like a district, like I showed in the previous map. So information from the utility, the historical record of outages and damage, historical weather conditions, and then all of the ancillary information, environmental conditions. We drive this with weather forecasts. So we want to be able to make these predictions days in advance. So most of our models run out 5 to 7 days in the future. And then we might want to predict different kinds of information. So a damage model would predict the number of poles that are broken, or the number of transformers that fail, or the amount of overhead line that is downed by things like high winds or ice. An outage model says how many outage orders are there, how many trouble spots are there where they need to dispatch crews to. And then resource models focus on predicting the number of people that they need. And different companies want to focus on different parts of this, depending on where in their organization these models are being used and what information the decision makers need to make those decisions. So this is just a visual example of what our feature database might look like. This one has around 300 variables in it. And so for one utility operating company, so where I sit in Columbus, Ohio, our electrical utility is AEP Ohio. So for AEP Ohio, this is what the feature database might look like. And so this is why machine learning and artificial intelligence methods are ideal, because we have a highly nonlinear system where the data are not normally distributed, where we're very interested in the extremes. And so the traditional methods of statistics probably don't do too well in these kinds of models. We update our models 4 times a day. So every 6 hours when new numerical weather prediction guidance comes out. And the ideal spatial resolution, so as this is a part that if I'm presenting to an electrical utility, I may not focus on as much, but here with a more GIS and geographical audience, you can appreciate the importance of spatial resolution and how that might impact the performance of the models. So I'll talk about that a little bit later. So what about the methods? So this is a very busy table that I don't expect you to read over Zoom, but it's just to illustrate based on past work and what a previous PhD student of a colleague of mine did as part of her doctoral work, is to summarize all of the ways that this has been done in the literature in the past. And so in this particular paper that was published in IEEE, Transactions on Power Systems, we compared all of these different methods and some new methods to determine which works the best for this particular application, one particular utility focused on looking at thunderstorm-induced outages. And so you can see there was many different types of models, and often we find that using a 2-stage or 3-stage model is really helpful. So in the first stage, we might predict what is the probability of there being an outage at a particular location. So for a particular grid cell or for a particular polygon, what is the probability of an outage for that day conditioned on the weather forecast for that day? In the second stage, then we're interested in explicitly forecasting the number of customers interrupted or the number of outages or the number of crews that might be needed in those. And then the other thing that we've spent a lot of time on is resampling and cost-sensitive approaches for training these models. So with resampling, we're trying to, on the vast majority of days, there is no weather-related disruption. So we call those blue sky days. And on blue sky days, that's thankfully the majority of time. But those aren't so interesting to an electrical utility because they don't need to do anything particularly different than normal operations. They're very interested in the rare but high impact events like a superstorm Sandy. But you're only going to have that once in your entire data set. And so how do you actually train the model to identify and accurately predict on future days that might be similar to that? And so the methods that we have tested are related to resampling, where we oversample the minority class, so those extreme high impact days, and undersample the majority so that we can rebalance the data set and better get at how better train models that can respond not just on the low impact days or the moderate impact days, but on the very worst weather days. So this is a quick summary of what we found. So on the graph right here, we show model performance in a number of different ways. First, we can look at the mean absolute error as a function of the overall MAE. And this overall MAE, you can see that the null model has a pretty high error as compared to the others. But in some other, if we slice and dice the data another way, we can actually see that there isn't as clear. The null model actually is sometimes hard to beat, because if we're guessing 0 pretty frequently, then we might do pretty well, since most of the days are blue sky days. So mean absolute error may not be the best way of scoring models. Instead, in this paper, we use the continuous ranked probability score because we're interested in making probabilistic predictions. So we actually predict the entire PDF of distribution so that we have predictions at the 5th percentile, 10th, 20th, 50th, 75th, 95th, 100th, all the way through the distribution. And so that we can not only give a best estimate, but give uncertainty around that estimate, and that we can see how that uncertainty changes conditioned on the weather forecast. And so here we can see that clearly then the null model does not do very well, and that we get things like our cost sensitive quantile random forest, or our random forest, quantile random forest models that do better. So another thing that is really important in doing this kind of model development, so this is a comparison of different approaches for developing now models for hurricanes, and comparing a 3-stage model to some of the other previous best models that we had found. And you can see in this case that we have discretized the service territory into really small grid cells, and that the color here is a function of the number of customer outages in each location. And we're comparing each of the models to the actual. So the actual is the first map here, and then each of these models that are labeled based on when they were published or who published them, to see which one does the best. And there's lots of details here that I'm going to kind of skip over, but we redid this for lots of previous hurricanes using a storm holdout. So where we withhold Dennis and train on the remaining hurricanes and predict that one to see how well it does in out of sample predictions. And that's one thing that, based on experience, we found to be really important, which is not a surprise, but that we can, with machine learning models, get an arbitrarily good fit if we include all of those days or cases within the model. But we're most interested in the out of sample performance. And so we spend a lot of time trying to make the model fail in different ways. So splitting the data in random holdouts, so 80% in the training, 20% in the validation, bootstrap that and repeat it thousands of times to get a better estimate of the performance in the holdout. We could maybe train it on one operating company. So train it on AEP Ohio and then run it on Indiana, Michigan, and see how well we can do when we hold out an operating company. We can also hold out a particular storm, like I showed on the previous slide, or hold out a year. So train it on all of the data through 2021 and then predict every day in 2022 and see how well the model does. And so the goal here is to identify the model that's going to work best on days that it hasn't seen, since this is a real-time operational prediction. And of course, you might get different results if you don't do it that way. So what does an overfit model look like? So this is a prediction of outages for Superstorm Sandy for First Energy. And this is including Superstorm Sandy in the training data set. You can see that most of the districts here fall along the 1-to-1 line and that we get a very, very close prediction. So there were 2 million customers actually interrupted, and the model between the 50th and 75th percentile nicely brackets that. But of course, that's not how well the model would do if another Sandy-like storm occurred. And so when we withhold Sandy, we can see that our prediction range increases greatly. So the 50th percentile from our probabilistic models is 1.3 million, and the upper estimate from the 75th percentile is 3.4. So much greater uncertainty. The actual number, 2 million, still falls within that range, but that indicates what happens when you exclude data from the sample. So how well do our models do? And this is an example from one of the electrical utilities. This is data running from October of 2019 through January of 2020. The actuals are the black dots. So that's the truth. What actually happened, we don't know that at the time that we make these predictions. And then what our model predicts is this solid blue line in the middle, and the uncertainty around that prediction is shown with the red or maybe looking pink shading. And we can report things like the bias. So a perfect model would have a value of 1, a correlation, higher the better, and then some error metrics where we want those to be as low as possible. And so we can see that this is the kind of scorecard that we would give to our utilities every month. We can also apply these methods not just in the United States. So this is an example that we did for China Southern Power Grid and part of the Guangdong Power Service territory for 3 typhoons that affected them. Here it's looking at pole damage for these 3 different typhoons. And again, if our model is perfect, all these points would fall along this 1-to-1 line. You can see that for some typhoons, it does reasonably well. For other typhoons, there's more error in the models. So let's look at an example from the United States to kind of get a sense for what information the electrical utilities have as they're going through their decision-making process. This is for Hurricane Hannah from July of 2020. And this shows the location of the center of circulation on the 25th. And so we can walk through what these predictions look like. So starting on July 22nd, when the storm was out here, we can see that this was forecast to be pretty weak. These wind gusts are something like 20 to 30 miles an hour. So that shouldn't really cause a lot of damage for AEP Texas. But as we step through these predictions. So here's the prediction that we made, a median of 21,000 customers interrupted based on the 0Z forecast on July 23rd. And what actually occurred was almost 270,000 outages. But as we walk through this, you'll see that for Hannah, the intensity of this storm really ramps up as we move from the 23rd to the 24th. So one day before, a median of 21,000, and then the next day a median of 101,000 with an upper estimate of about 498,000. You can see how that's distributed amongst the various districts here and how these wind gusts now are all in the 60 to 70 mile an hour range. And then if we step another day ahead and look at how the forecasts change, you can now see that our 75th percentile is closer to what actually occurred here in the state of Texas. But of course, the electrical utility, just a day before this event, doesn't have a lot of time to respond to or to adjust to those changes in the intensity and track of the storm. And that kind of uncertainty is inherent within the system. So if we compare the accuracy overall, we can say that the 75th percentile from our models looks reasonable, and that we also get, so we have the actuals by district in the left-hand column, and our model predictions from the 75th percentile, which is what we typically use for the higher impact days. And then we can look at the performance in the whole month of July of that year and look at the correlation and bias. So we slightly underestimated, and the error is a little bit higher, but the correlation was pretty good in terms of where and when the maximum interruptions occurred. So what this example highlights is issues related to uncertainty. There's a tremendous amount of uncertainty in making these forecasts. There is uncertainty in the weather forecast itself. We don't always know where and when tornadoes or severe weather or hurricanes are going to make landfall. There is uncertainty in all of the non-meteorological model inputs as well. And there's uncertainty in the prediction model that's conditional on those inputs. And as I'll show in a moment, also the spatial and temporal resolution of the modeling that we do also affects the performance. And so how can we characterize and communicate this information to decision makers so that they can make better decisions even under deep uncertainty? Here's an example of what that uncertainty might look like. We have the spaghetti plot of models shown for Hurricane Gustav as of August 25th, 2008 on the left, as of August 29th, 2008 on the right. We can see on the left, there's a tremendous amount of uncertainty in the track of that storm based on where it was at that time. And so depending on which of these models you think is the most accurate, you could get things that were in very different geographic locations. And so that matters if you're an electrical utility in Florida or Alabama or Louisiana. By the 29th, we had a lot more consensus in where that storm was going to make landfall. And so that's one example of how we can take all of the information from these various models and make a prediction of the power outages for each condition on each individual model and communicate that to the users. So there is this Monte Carlo wind speed probability product that generates 1,000 forecast realizations based on historical track and intensity forecast errors. And we can use those 1,000 ensemble members and run a power outage forecast for each of them. And so this summarizes what our prediction would have been. This is outages now, not customers interrupted, but trouble spots. So each one of these could be a few customers or hundreds or thousands of customers. And this is for Hurricane Katrina. And so if we just use the National Hurricane Center best track, we get a value of around 7,000 outages. If we use, this histogram shows running it for all of those 1,000 ensembles. And if we take the ensemble average, we end up with something around 8,800. And that is a lot closer to what actually occurred in this particular utility, which is around 10,000 outages. And this also indicates how much uncertainty there is, even at relatively short lead times, that it could have been relatively minor if the track would have shifted and the intensity would have decreased, or it could have been many times greater. So rather than 10,000, it could have been 20,000 outages, twice as great a magnitude if the track would have shifted and the storm would have intensified to bring the strongest winds through the service territory of this particular utility. So we attempt to characterize and communicate all of that uncertainty to show the range rather than just a single best estimate that exists. So I'd highlighted before this idea of spatial resolution. So just to quickly give a couple of examples, this shows the service territory for AEP Ohio. This is a 5-kilometer grid cell, and this is showing model predictions made based on models trained for each one of those grid cells. Same day, and this shows now the polygons that are the districts for AEP Ohio. And so if we compare the error from this map on the left to the error from this map on the right, we can see that doing it at the grid cell level and then rolling it up to districts and comparing accuracy at the district level, we have an error that's around 3,100. This is in customers. And if we develop, train, and validate models at the district level, even though we're communicating ultimately information at the same resolution, we have an error that is about a third of what it was based on this finer resolution. And that is relatively consistent. It's not specific to this particular day or to this particular utility. And so even though sometimes we think that we really want to drive this down to a finer and finer spatial resolution, depending on the information the decision makers need, it might be better and more accurate to do this modeling at a coarser resolution. So if there's questions, I can unpack that in the discussion a little bit more. We did this in other places and found the same thing, that we can do things at a couple kilometer resolution, at 15 kilometers, so kind of zip code resolution, at 40 kilometer, kind of like county resolution, and that we see R squared increases and error decreases as we go from finer resolution to coarser resolution. So to kind of summarize what I've presented today, we've been working on developing power outage models to support decision-making. And this is specifically for electrical utilities, but it could also be used to support state and federal emergency management agencies that are thinking about things like evacuations prior to storms or other mitigation or hardening kinds of investments. And these types of models can be adopted to many different kinds of weather systems and to hazards. Things like wildfires also are a huge driver of what's going on. And there is a tremendous amount of uncertainty. It doesn't matter how advanced the machine learning modeling, how massive the feature data set, how long the time period, there's always going to be uncertainty. And so it's really important to think about how we characterize, quantify, and communicate that to the decision makers that are making real decisions with these tools every day. And so there's a lot of interesting science here, but there's also a lot of interesting applications when we think about the research to operations continuum. And so one of the things, so what I'll close with is just a brief summary of my journey in this area. And like probably many of you, being within the university environment, a lot of my time and effort went into research and into sort of focusing on intellectual merit and publications and NSF type grants. What I realized is that there's also a tremendous opportunity for us to translate what we're doing in the academy to the commercial sector. And now more than ever, there's demand for skills that geographers and those with geospatial training can bring to industry, and more of my grad students, and perhaps more of the graduates from geography programs, are ending up in industry, which I think is great. And so last year, we licensed the technology that we developed. So some of the things that I showed you in the presentation today, we licensed them from the university and started a corporation called Storm Impact. This was founded by myself, the postdoc who was working in my group, and a computer scientist who did all of the front end web interface that we provided to utilities. And so now we are focused on building a company around this technology and really selling it to new utilities, coming up with new applications and products. We received some funding from NASA through their SBIR program to do some R&D, but all within the commercial sector. And so it's pretty cool. I like learning new things all the time, and I know very little about the business world. Thankfully, I've been able to hire really good people that can help and inform and mentor us in those areas. And I think there's a lot of opportunities for faculty who are interested in taking the plunge into the commercial sector. And so just putting it out there as a challenge or opportunity that if you're doing interesting science, but you want it to be put in the hands of decision makers, there's definitely opportunities at many universities and ways to do that. And also federal funding to support some of that translation. So with that, I will stop there and open it up to questions and comments. And I thank you for your attention.
Thank you so much, Dr. Quiring, for the excellent sharing. This is a very interesting talk. So I guess we have the few participants who stay here. So if you have any questions, you are welcome to post your questions in your Q&A button in the chat box, and then I'll be able to read the question, and then Dr. Quiring will answer those questions. So let's see. Yeah, so there is a first question is, first, thank you for your talk. It was very interesting. It's actually from Yun Jun. I hope my pronunciation is correct. So it says, I learned so much. And the first question is, can I ask about the data source you used for your model and if it is open to the public?
Yeah, great question. And many of the data sources that we're using are in the public domain. So all of the meteorological variables, all of the environmental conditions, soil moisture, soil conditions, vegetation, all of those things are from NASA or NOAA or other places that commonly as geoscientists we might go to. The thing that is proprietary in these models are the data from, so the information that shows where every single customer is, so their addresses, the information on the power system, so the poles and transformers and where those are located and what type they are. And so those things are not freely or publicly available. But the Department of Energy and the Department of Homeland Security actually put up a lot of information that is publicly available around the US power infrastructure. And so it would be possible to do something similar to this using only publicly available data.
Thank you so much. And there is another question from the same participant. Secondly, also, it seems like the model sometimes overestimates or underestimates. So did you have a chance to compare the ratio of overestimation and the underestimation of the model?
Yeah, great question. I don't have a number off the top of my head to answer that particular question. However, I can say that we really looked at scoring performance. So often from the utility perspective, they're not so concerned about the absolute number. They're interested in, is it in the right bucket? So on a day where there's a blue sky day where nothing's major is going to happen, does the model say, yes, this is going to be a blue sky day? And so do we score the performance? Do we indicate and separate the low, moderate, and high impact events? So we do, in our monthly performance report cards for the electrical utilities, break out performance so that we're reporting it not on all days, but on days based on different thresholds. And each utility sets its own threshold for what they consider a major event. And so we want to especially tune and make sure that the models are accurate on the high impact days. And so because there's relatively few of those, we need to aggregate them over a longer period of time. And I guess not surprisingly, there are some biases that exist in the models, and that in general, we would see that the likelihood of overestimating is going to be greatest in the lowest magnitude categories on those blue sky days, and the likelihood of underestimating tends to be greatest on the high magnitude days. But we also see that there's a greater spread. So we're reporting a single number, a best estimate, as well as an uncertainty. And we can see that so it's like, this is off the top of my head, but something like 90% of the time, the actual falls within the confidence intervals around our best estimate. And so we can't always give them an exact number, but we can with high confidence tell them sort of what the range is going to be.
Thank you so much for answering the question. I think other participants probably still think about the question. So we have another one. It's from Dr. Lai Yinzhu, and he said, "This is a great talk and thanks. I have a technical question for the validation of the model. It is an excellent idea to compare the quantiles of the prediction. Are they based on the holdout predictions? How large the prediction sample is generated?"
Yeah, great question. Thank you. So the validation is based on the holdout, and the sample size can be determined based on how we do the holdout. So as Lion knows, we sometimes use an 80-20 or a 70-30, and we can repeat that lots of times. And so we can calculate and compare things on that entire holdout sample and do it many times. So the answer is kind of like, it depends on how much time and effort you want to spend and how large and robustly you want to do that holdout validation. But yes, absolutely want to score and compare the distributions, not on what the days that the model has seen, but on the days that the model hasn't seen.
Thank you so much for answering this question. So maybe I can take advantage of being the moderator to ask one question, which I'm very interested in, is about the scale issue in geospatial modeling. So as far as I know, most of the data, especially the electrical system data, were defined by humans. So it follows the administrative boundaries. However, the impact of a storm is not followed by the administrative boundaries defined by humans. It is shaped by the nature. So you mentioned in one of your slides, which is a very interesting part, is that you consider deciding the best spatial and temporal scales for the analysis. So could you elaborate a little bit more on how did your model or your research approach determine the optimal scale of the modeling process?
Yeah, excellent. So I think there's a lot of interesting research that could be done related to this spatial and temporal scale issue. And as you note, when we think about scale, we as scientists, we might want to model things at the optimum scale for quantifying that physical process. But in this case, it's not so much about generating knowledge or understanding of the physical process, but of deciding things based on what is the information need of the decision maker. And so how we approach this was from a very practical or pragmatic standpoint to say that there are a variety of different predefined spatial units of analysis. And these predefined spatial units of analysis, as you note, are human abstractions. They're things like zip codes or counties or districts that the utility draws. And so we have things that are kind of point data that we can re-aggregate at any spatial resolution. And then we have some gridded data sets that we can either aggregate or rescale, downscale, upscale to those same resolutions. And so we did this repeatedly at different, both doing it based on administrative boundaries like counties and zip codes and districts, but also doing it based on grid cells of different sizes to see how that affects the error and the performance of the models. And so it's not quite the way that we would probably want to do it for a pure sort of intellectual merit, like examining kind of the processes. It's more of a pragmatic to say, for the decision makers, they kind of give us, here's the units that we might use. And they have things that are operating companies, so kind of state level, districts that are multiple counties, and then things like OMS areas where there's multiple OMS areas within a single district. And so we compared fit models, trained and validated them on each spatial resolution, and then compared to see how that influenced the accuracy in the holdout validation. So yeah, I don't know if that fully answers your question, but that's the technical approach that we took. And the interesting part is that there's initially the utilities wanted it at a very fine spatial resolution. They're like, okay, give us a model at like 1 kilometer or a few kilometers. But what we showed them is that that actually doesn't give them the best answer. And they're really not allocating people at that resolution anyway. They're sending them to like an operating center or a yard where the trucks park and the equipment is. And so they don't have those at in every 1 kilometer grid cell. They have a few per district. And so that was really, yeah, so that's how we did the analysis.
Thank you so much. I think that explains a lot, especially considering the potential customers of your products, rather than simply thinking about the scientific scale of this operation of the storm. Yeah, thank you so much. I'm not sure if there's any other questions from the audience. Maybe I can take advantage of being a moderator and ask one more question, and we're almost at the time to finish. Yeah. So I have one very general question is, I really like the products and also the idea of modeling the impacts, especially the power outage caused by storms. So could you give one detailed use case of how the stakeholders, or like you mentioned, decision makers, can make more informed and efficient decisions based on the data products you provided from the model?
Yeah, absolutely. So a common decision that our customers are making today is tomorrow in Ohio, there's forecast to be an increased number of power outages from the system that's going to move through overnight and through the morning. And so they're deciding how many people they're going to make work this weekend. So how many people are going to get overtime this weekend and be asked to work and stay here? And also, do they have enough utility crews? Do they have enough people on staff this weekend to respond to the storm? Or do they need to bring in contractors or people from other neighboring utilities. So from other states that maybe aren't going to be affected by this power system or this weather system. And so that is the type of decision that our particular customers are making. They might also be interested, if we ran these models over a longer period of time, in making decisions about where they should spend money hardening their system. So if they found like, hey, there's this one, it's always in Bryan, Texas, that we have the outages. And so we're going to spend money on replacing poles and undergrounding line in this particular neighborhood or this particular district because the frequency and severity of outages is so high in this location. So that would be kind of on the long-term risk mitigation side, a decision that they might consider.
Thank you so much. Yeah, I think we're a little bit over the time of our 1 hour webinar. But again, I want to express the sincere appreciation to Dr. Stephen Quiring for sharing this wonderful talk. And also, I think we're going to share the recording afterwards. So I guess more people will benefit from your excellent presentation today. Thank you so much for your time. And thanks everyone who joined us today to listen to this wonderful presentation. And Amy, I think we can stop the recording and yeah.